Hey there, high school chemistry students, and welcome to The Explainer. If you've ever stared at a massive jumble of element symbols and just wondered how on earth you're supposed to connect them, well, you are definitely in the right place. Today, we're going to demystify exactly why atoms bond in the first place, and I'm going to give you a foolproof, step-by-step mathematical recipe for drawing those tricky Lewis structures. Okay, let's dive into this. Think of me as your guide today. Here is our game plan. First, we'll cover the quest for stability, then types of chemical bonds, third, the octet rule, fourth, drawing Lewis structures, fifth, calculating formal charges, and finally, we'll wrap it all up with a pop quiz challenge to test everything you've learned. Let's kick things off with Section 1, the quest for stability. Have you ever wondered why atoms don't just fly around solo in the universe? Like, what makes them actually want to link up? Well, a chemical bond isn't just some physical stick holding two spheres together. It's a force. And the absolutely crucial point here is that it's a force accompanied by a decrease in energy. You see, in nature, lower energy basically equals higher stability. Molecules form simply because hanging out together represents a much more stable, lower energy state than being individual, isolated atoms. Nature's, kind of lazy. It always wants to relax into the lowest energy state possible. And that brings us to the classic concept of why bonds form. Think of the noble gases, helium, neon, argon, as the Zen masters of the periodic table. They already have a perfectly stable electronic configuration. They are at minimum energy, so they simply don't bother participating in bonding. They don't need to. Every other atom on the periodic table looks at those noble gases and says, man, I want to be exactly like that. They combine with other atoms specifically to acquire that coveted noble gas configuration. Now, modern chemistry views this as a microscopic tug-of-war. Step 1, as two atoms approach each other, the positive nucleus of one atom pulls on the negative electrons of the other. But wait, step 2, both positive nuclei push away from each other, and those negative electron clouds repel each other too. So it's this massive battle of attraction versus repulsion. Step 3 is the magic moment. If the net result is attraction, the total energy of the system drops, and boom, they fall into a comfortable lower energy hammock, and a chemical bond forms. Okay, let's move to Section 2 and see how this builds. Types of chemical bonds. Depending on the elements involved, atoms take completely different paths to get stable. It really comes down to an element's personality. Is it electropositive, meaning does it readily give away electrons, or is it electronegative, meaning it eagerly accepts them? When an electropositive atom meets an electronegative atom, they form an ionic bond, and that releases a massive amount of energy, over 42 kilojoules per mole. But if you have elements that just want to compromise and complete their outer shells together, they form a covalent bond by simply sharing those electrons. All right, moving right along to Section 3, the octet rule explained. Remember our Zen master noble gases? Well, with the exception of helium, they all have exactly 8 electrons in their outermost shell. That is the magical number for stability. 8. Every other atom out there is going to hustle. They'll lose, they'll gain, or they'll share electrons, doing literally whatever it takes to complete that octet and reach that perfectly balanced ns2p6 configuration. So, how do we actually show this? Section 4, drawing Lewis structures. It's time to put the theory into practice. I know. This looks like a lot of algebra, but I promise it's an incredibly logical, foolproof recipe. Let me signpost these 4 math steps for you. First, find N1. This is just the total number of valence electrons you actually have available. Simple enough? Next, N2 is what you want. Every hydrogen wants 2, but everything else wants 8. Step 3, N3, is simply the difference between what you want and what you have. Just subtract N1 from N2, divide that by 2, and that tells you exactly how many bonds to draw. Finally, N4 is whatever electrons are left over. Subtract N3 from N1, divide that by 2, and you've got your lone pairs. We're going to walk through an example in a second, but maybe pause right here and copy this down if you need to. Okay, so once you do the math, how do you know what to actually draw? You have to pick a central atom to build your whole structure around. And here's a secret trick for you. The central atom is either the one you have the least of or the one that is more electropositive. Never put the greediest, most electronegative atom in the center. Let's plug some actual numbers in for carbon dioxide, CO2. Carbon has 4 valence electrons, and each oxygen has 6. So N1, what we have, is 4 plus 12, which gives us 16. For N2, what we want, we have 3 total atoms that all want a full octet. 3 times 8 is 24.
Now for N3, our shared electrons, 24 minus 16 leaves us with 8 shared electrons. Divide by 2, and that means we need 4 bonds. Lastly, for N4, the unshared electrons, our original 16 minus the 8 we just shared leaves 8 unshared electrons. Divide by 2 again, and we have exactly 4 lone pairs to place. Let's see how this all comes together.
And this brilliantly illustrates our final structure. Carbon is our central atom because, well, it's more electropositive than oxygen, and there's only one of it. We knew we needed 4 bonds, so we put a double bond on each side, connecting the carbon to the oxygens. That satisfies carbon's octet perfectly. Then we take our 4 lone pairs and distribute them to the oxygen atoms so they get their octets fulfilled too. It just works out like a perfect puzzle. Moving right along to section 5, calculating formal charges. Think of formal charge as a way to balance the chemical books for each individual atom. It's how we check our work. The formula is beautifully simple subtraction. Take the normal valence shell electrons that an atom should have, minus the number of bonds currently touching it in your drawing, minus the number of unshared lone pair electrons sitting right on it. That's it. Check this out. Let's compare a neutral molecule, like ammonia, with a positive polyatomic ion, PCl4+. For ammonia, NH3, when we do that subtraction, both nitrogen and hydrogen end up with a formal charge of exactly 0. That is, perfect stability. But look at PCl4+. If you zero in on phosphorus in the center, it usually has 5 valence electrons. But in this structure, it has 4 bonds and 0 lone pairs. So 5 minus 4 minus 0 equals +1. The math perfectly scales up, proving exactly why the overall ion carries that positive 1 charge. All right, section 6, pop quiz challenge. Let's see what you've really learned. Here is your rapid fire challenge. I want you to look at the negative polyatomic ion, NO2-. Using the exact rules we just covered, which atom goes in the center, and what are the formal charges on all the atoms in your final structure. I strongly encourage you to pause this explainer right now. Grab some scratch paper, calculate your N1 through N4, and try drawing it out yourself. Okay, are you ready for the reveal? Nitrogen is your central atom because it's less in number and more electropositive than oxygen. When you draw out the structure with its bonds and lone pairs, the formal charges balance out to nitrogen being 0, 1 oxygen being 0, and the second oxygen carrying in -1 formal charge, which makes total sense because it accounts for the overall negative charge of the whole ion. If you got that right, massive congratulations. You have successfully navigated the complex rules of chemical bonding. As we wrap this up, I want to leave you with this final, kind of mind-blowing thought. Look around your room right now. Every single object you see, the screen you're watching this on, the desk you're sitting at, even the air you're breathing is held together by these invisible, microscopic tugs of war happening this very second. Millions of atoms constantly balancing nuclear attraction and electron repulsion just to find that stable hammock of energy. Chemistry isn't just numbers on paper. It is the invisible architecture of your entire world. So keep questioning, keep drawing those structures, and I'll see you in the next explainer.